Today's topic, parallel plate capacitor and expression for capacity of a parallel plate capacitor. That is the derivation of the expression or formula for the capacity of a parallel plate capacitor. Now this expression is actually derived directly from the definition of the capacity of any capacitor in general. So this is a very important topic from the both from the board examination point of view and also the entrance examinations point of view, problems of the entrance examination point of view, and more importantly it's very useful for the understanding of the working of a capacitor, on what factors actually capacity of a capacitor depends upon. All these things, practical understanding of a capacitor, how it's constructed, in what way it should be constructed, all the things can be understood from this particular derivation. That's the importance of the parallel plate capacitor derivation practically. Now this is very important from the board examination point of view. So carrying about 4 marks to 5 marks. So roughly around 4 marks mostly. So what is a parallel plate capacitor? So the definition. So any capacitor, now already we have seen the definition of a capacitor. It consists of a pair of conductors. A pair of conductors. Pair means two conductors. Here, if both the conductors are exactly identical plates, for example, the first conductor is a rectangular plate like this. I'm just drawing the plate this way. So just see here. Now this is the first conductor. It's a rectangular plate. So simply it is represented this way in the diagram. So this is the first conductor, and the second conductor is again an identical rectangular plate. So I'm just it's actually shown just by means of a single line. This line represents a rectangular plate. So exact diagram of the rectangular plate will be three-dimensional diagram. It should be drawn exactly speaking like this. I'll just take a rough column here, a small rough column. How the rectangular plate looks like? It looks like an exact rectangle. This way it's actually drawn. So let's see here this way. This way it looks like the rectangular plate. But this is a three-dimensional diagram, it's difficult to draw. So exactly parallel to this, another rectangular plate will be there. So this is a real three-dimensional diagram. But three-dimensional diagrams, it takes more time to draw. So it's actually better to avoid such diagrams this way. The two parallel plates will be, this is the first plate, this is the second plate. So instead of the drawing three-dimensional diagram, here just to the left plate is represented by a single straight line, the right plate. This is sufficient actually. This simple line diagram is sufficient for the sake of understanding derivation. So any complication comes, then the three-dimensional diagram will be helpful. Any imagination or any situation related to or any problem based on the parallel plate capacitor, this diagram will be useful to some extent. But most of the things can be very easily understood. All the actual scientific derivation is this simple diagram is sufficient. So the left plate is actually denoted as P and the right plate is denoted as Q. The same way here, the left plate is denoted as P and the right plate is denoted as Q. Now always any capacitor, so capacitor is nothing but a pair of conductors, two conductors. So this is the left conductor, first conductor, this is the right conductor, second conductor. Now these two conductors are actually charged equally and oppositely. We have seen this in the capacitor, definition of the capacitor. Now what's the purpose of a capacitor? A capacitor is nothing but a pair of conductors which is used for storing large amount of electric charge at very low values of potential. At a very low potential, each conductor actually stores a large amount of charge. Usually the left plate will be storing positive charge and the right plate will be used to store negative charge. So the importance of a capacitor is large amount of charge is stored on each conductor or on each plate at very low potential. That's the simple definition of the capacitor. Previously we have seen. So this derivation is entirely based on this definition of a capacitor and also the definition of the capacity of a capacitor. So the symbol for capacity of a capacitor is, already we have seen, symbol for capacity of any capacitor is known as C. So an expression for this C is actually what is required. So this is the left plate and this is the right plate. Now both these plates now are charged by means of a battery. So this is a lead wire. So I have drawn a lead wire from the conductor P. Lead wire means any wire that goes from the conductor to anything else, any other device like a battery. So this is simply called as a lead wire or a connecting wire. So this is a connecting wire. So similarly, this is a connecting wire, extension of the connecting wire from the conductor from the plate Q. So both these wires are now connected to a battery this way. So this is the simple diagram of the battery or a cell. So this is the positive terminal of the cell. This is the regular way in which a cell or a battery is represented. This is the positive terminal. This is the negative terminal. So positive terminal is connected to the plate P of the capacitor. Negative terminal is connected to the plate Q. So this is any regular capacitor, a pair of conductors which are used to store a large amount of charge at low potential is called as a capacitor. Now, if this pair of conductors are exactly identical rectangular plates, or they can be even circular plates also, but the thing is they should be exactly identical and they should be also parallel to each other. Like in this diagram, three-dimensional diagram, it's more easier to understand the situation, real situation, but the actual scientific theory, this is sufficient. This simple diagram, line diagram, which is a simple two-dimensional diagram, is sufficient for the sake of understanding of the scientific theory. So if the two plates are identical plates which are parallel to each other, then the capacitor is called as a parallel plate capacitor. Parallel plate capacitor. So this is a simple definition of the parallel plate capacitor. Now, aim is to derive an expression for the capacity of a parallel plate capacitor from the definition of capacity. Already we have seen the definition of capacity. C is equal to, what is the formula for capacity? So this is also the defining equation. This is actually the equation using which capacity is defined. It's the charge on each side, left hand side, right hand side, charge on each side divided by potential difference between the two conductors. That's how capacity is defined. So based on this definition, a real formula for parallel plate capacitor capacity is actually can be derived here. So that's the aim of the derivation here. So now once the battery is connected to the two plates, the battery, what it does is immediately charges the two plates equally and oppositely, exactly equally and oppositely. So left plate is charged because it's connected to the positive terminal of the battery. Left plate will be charged positively this way, and the right plate will be charged negatively. Now the important thing is both these plates will be charged equally and oppositely. The reason for this is, suppose equally and oppositely means supposing left plate has 5 units of charge, right plate also will have 5 units of negative charge. That way both the magnitudes of the positive and negative charges are equal, but their signs are opposite. So why the two plates are getting equally and oppositely charged? The reason is a battery, once it is connected to the two conductors, immediately battery draws positive charge from the right plate. The plate which is actually connected to the negative terminal actually removes a certain amount of charge. It is called as drawing the charge. Drawing means removes. It takes charge from this plate. Initially both the plates are neutral, they don't carry any charges. Once this plate is connected, right plate is connected to the negative terminal, the battery, what it does is it removes charge from the right plate. Say 10 units of charge it removes means, then these 10 units of charge the battery actually sends or pumps into the left plate, the plate which is connected to the positive terminal. So 10 units of charge is added. So we are considering only positive charges. So actually electric current is actually assumed to be the flow of positive charges. So everything in electricity is explained using positive charges. So assuming only positive charges, the battery actually removes 10 units of positive charge from the right plate and adds these 10 units of positive charge to the left plate. So left plate gains 10 units of positive charge, so charge developed on it is plus 10 units. But 10 units of charge is removed, positive charge 10 units is removed from this plate, means it develops minus 10 units of negative charge. That way the two plates will be getting equally and oppositely charged. So charge on each plate is exactly the same. So this plate is plus Q, means automatically right plate will be minus Q units of charge. That's how a battery functions once it's connected to the two plates of the capacitor. So immediately an electric field is actually established between the two plates. Now one very important thing is when positive charge is actually supplied to the left plate, so this entire positive charge, usually to any conduct plate, if we supply a positive charge, supposing we have one plate here, I'm drawing another rough column here. So rough columns are very useful. The reason is the reasons of the particular derivation, scientific derivation, the reasons actually belong to certain other topics related to this lesson or even previous lessons. Those reasons, it will be very useful to understand the reasons in the rough column because they don't really belong to this top. They need not be written in the answer, because every answer, essay answer, even maximum marks essay answer carries only 5 marks. So only 4 to 5 points must be explained. All the detailed reasons are not required. This time will not be there for writing and also for correction of the answer by the faculty or by the teachers. So simple manner, only 5 points maximum should be written. So all detailed reasons will be useful only for the sake of understanding and for solving complicated problems. Very, very complicated problems they can solve very easily by using the detailed reasonings or detailed reasons. So when charge is given to any conductor or a plate, so actually charge will be distributed on the plate on both sides. So on both the sides, charge will be actually distributed. Here also the same thing should be happening, but the reason is why charge is present now only on the inner face, not on the outer face. The reason is the charge on the negative plate will attract this positive charge. So whatever charge that is found even on the outer surface, outer face of this plate, that means left face of this particular plate, it will be actually immediately attracted by the negative charge and it comes entirely to the inner face. The same thing will happen here also. The negative charge on the plate Q also, even if it's initially formed on the outer face, this side, I'm just showing with the cursor. So everyone must compulsorily observe the cursor. Immediately, because of attraction by the positive charge, plate P, the entire negative charge will be coming and settling down only on the inner face. So no charge will be present on the outer face at all for the plate P as well as plate Q. Whatever charges that are found, plus Q and minus Q, they will present residing only on the inner faces. This is a very, very, very important feature of any capacitor or any parallel plate capacitor or any capacitor. Charges are present will be settling only on the inner faces. No charge will be present. Even little amount of charge also will not be present on the outer faces. So that's a very important feature. Now the important thing is, now always electric field will be directed from the positive charge towards the negative charge. So this the left plate is positive, right plate is negative. So electric field direction will be like this. This way its electric field is directed. So the electric field vector or the electric field intensity is denoted by symbol E. So its direction is exactly from the left plate towards the right plate, because direction of electric field is always away from the positive charge and towards the negative charge. And very, very important thing is, in order to have very high value of capacity for a capacitor, always the two plates are kept very, very close. So only in the diagram it is actually shown that right plate is actually far away, considerably away, well away. But really speaking, in practical real life situation, the capacitor will be more effective. These two plates are very, very close. So if you take any point, this point will be really between the two plates, means compulsorily it will be each plate is almost touching the other plate. So the point, any point, real point will be very, very close to the plate. So because of its closeness, because the pointer to the pointer, because it's very, very close to the plate, this plate appears to be of huge dimensions, huge size, huge area. So roughly practically each plate can be taken to be of infinite area. So already we have seen that if a plane sheet is considered, a plane sheet like this, carrying a certain amount of charge, say positive charge or negative charge, at any point, if the plane sheet happens to be of infinite area, at any point near it, at a point say P near it, electric field will be exactly uniform, exactly directed perpendicular to the area of the plate. If it is positive charge, is directed away from this. We derived this electric field. What is the formula for the electric field? It depends on the surface charge density near a plane sheet of charge, infinite plane sheet of charge, sigma by 2 epsilon naught. This was a very, very, very important formula which we have seen in the application of Gauss law, the second application of Gauss law. So the electric field entirely depends upon the surface charge density. It is independent of distance at all points. For an infinite plane sheet, electric field is uniform exactly depending on the surface charge density. So the same thing happens here also. Near the positive sheet, electric field will be uniform. The same thing happens even with the negative sheet also. At all points, electric field is uniform. So the field due to the positive sheet, you call it as E1. Field due to the negative sheet also, you call it as E2. Resultant field will be E1 plus E2. It will be, that is, E1 bar plus E2 bar. So depending on the direction, if they are in the same direction, they can be added. If they are in the opposite direction, it will be E1 bar plus E2 bar will be two vectors. If they are in opposite directions, P bar plus Q bar will be P minus Q. If P bar and Q bar in the same direction, two vectors, say P bar and Q bar, if they are in the same direction, then magnitudes will get, resultant vector will be the sum of the two vectors. If they make an angle theta, then how to find out the resultant? We know the formula, square root of P square plus Q square plus 2P cos of parallelogram law of vector addition has to be used. So using that technique, the resultant field in between the two plates can be determined. But the important thing is whether it's positive sheet or negative sheet, both the fields will be uniform, because both the sheets, both the plates will behave like infinite sheets. So always near an infinite sheet, again come back to this diagram in the rough column, near an infinite sheet electric field will be uniform depending entirely on the surface charge density. So this is the thing here. Now once we get an electric field, once we can find a formula for electric field, net electric field between the two plates, automatically we can find out the potential difference between the two plates. And once we find out the potential difference, just applying this formula, just look here, applying this formula we can find out the capacity of the parallel plate capacitor. That's the method of the derivation. So entire derivation is very simple, just by using the regular formulae or regular concepts which you have seen earlier, easily this can be derived. So now what is the net field here? So net field here, now just observe here, the electric field near a infinite plane sheet of charge entirely depends on the surface charge density. And what is the formula for surface charge density? So surface charge density, very simple formula we have seen, charge divided by area. Now both the plates here, metal plate P and the metal plate Q, what are the charges on them? Charges magnitude is same, Q and Q. Ignore the signs. And what is the area? Both the plates are of identical dimension. That means both of them have same area. That means surface charge density on each will be exactly same. This means that electric field due to each plate will be exactly same in magnitude. But what about their directions? Always electric field near a positive plane sheet of charge will be directed away. What if the plane sheet of charge is negative? Electric field will be directed towards the negative charge, negative plane sheet. So applying this here, the net electric field easily can be determined. So whatever things we are seeing here are simple, nowhere any complication is there. Now just see here, first we'll have to find out the net electric field. So what is the net electric field here? The first electric field or electric field vector due to the positive plane sheet of charge, you call it as E1. So what is the direction of E1? It's directed away from the positive plane sheet, that means towards right. And next, the electric field due to the negative plane sheet at the same point, we are taking a point, same point due to the negative plane sheet, what is the electric field or electric field vector due to the negative plane sheet of charge? That is due to the plate Q. You call it as E2. But what is its direction? Its direction will be towards negative sheet. That means that's also towards right. This is very important, most important point in this derivation. So the field E1 due to the positive plane sheet of charge is rightwards, and the field E2 also is rightwards, because field E2 should be towards negative charge. That means that also is rightwards. That means net field will be simply the sum of, because they are in the same direction, exactly same direction, net field will be E1 plus E2. So this is the very important step. Now what about each value? Now apply Gauss law. Now from Gauss law, we already seen this particular formula. The electric field near a plane sheet of charge is sigma by 2 epsilon naught. So the electric field due to the positive plane sheet of charge is simply given by sigma divided by 2 epsilon naught. And what about E2? E2 is also given by surface charge density. E2 is the field due to the negative plane sheet of charge. So that's also given by surface charge density sigma divided by 2 epsilon naught. Now in both cases, sigma is same, because sigma is what? Charge by area. So sigma being same, E1 and E2 are equal. So the very next step is, what we are getting is, as sigma is same as sigma, which is what is sigma? Q by A is same for P and Q. What does this mean? This simply means that E1 is equal to E2 is equal to sigma divided by 2 epsilon naught. So then what happens now? Substituting this here in equation 1. So 1 implies E is equal to E1 plus E2 can be written as E1 plus E2 is what? Same as E1. So E1 plus E2 now can be written as what? Simply I am writing just E1 again, because E1 and E2 are equal. So that is equal to 2E1. So that is equal to 2E into E1 is what? Here sigma by 2 epsilon naught. So then what is happening here? 2 getting cancelled. So simply it's coming as sigma by epsilon naught. So therefore the net electric field we got. So this equation is very important. We directly got it from Gauss law. So once we got this, what is the potential difference now? So the potential difference across the two plates, we call it as V. I'll just write this more clearly. The potential difference across the two plates, just call it as V. So this potential difference is really V between the two plates is actually applied by the battery across the two plates, because battery itself is forming these charges. Only because of the charges present on the two plates only potential difference exists, or electric field exists between the two plates. So potential difference across the capacitor, that means two plates, V is equal to ED. Now this is a very important relation between potential difference and electric field intensity. This is applicable in any uniform electric field. Now the electric field between the two plates is uniform. So call the plate area of each plate as A. Now the distance between the two plates, we call it as D. So potential difference between the two plates, that means we are taking the two plates, potential of the left plate we are considering, potential of any conductor is nothing but potential at a point very close to the particular conductor. Similarly, potential of the right plate is nothing but potential at a point very close to the right plate. So take 2 points very close to the two plates inside only. Then the potential difference between these two plates itself is called as, the potential difference between these two plates is nothing but potential difference between these 2 points very close to the two plates. So that potential difference in the uniform electric field is given by electric field into distance between the 2 points. Distance between these 2 points very close to the two plates is nothing but distance between the plates itself. So this formula now can be used. So ED, so that way we got E is equal to sigma by epsilon naught. So E is nothing but what? Electric field. We got already sigma by epsilon naught into D. So now just observe here. So whatever things we are seeing here are simple, nowhere any complication is there. Okay. So thus in this equation for potential difference, V is equal to ED. So we got a sigma, in place of E we substitute the equation to sigma by epsilon naught into D. So here surface charge density already we know. So this is the rough column, just see here. So I have written some very important steps required for the derivation in the rough column here. So this is actually a regular definition of this is a simple definition for surface charge density. Surface charge density on any surface, when charge Q is distributed on an area A, then charge divided by area gives charge per unit area. This charge per unit area itself is called as surface charge density. So this is actually the definition for, or the defining equation for surface charge density. And this is also rough column. So compulsorily rough column must be shown as rough in the classwork. So it's actually better if the rough column is on the extreme right, because there is no place here. I have written actually in the middle. So this is also actually a rough column. This is also rough. Actually there is no thing here. So rough I am putting. So later I'll just this part I'll just remove. So it will be clear that it's rough column. Rough columns are very important because the reasoning steps we are considering in the, I'm just showing in the rough column. So without reasoning there will not be any proper understanding. The reasoning steps usually will be definitions, very simple definitions, or very simple results obtained from very simple laws. So this is actually a very important result obtained from Gauss law. The electric field vector or electric field intensity near a infinite plane sheet of charge. It depends only on the surface charge density sigma and given by sigma by 2 epsilon naught. So this, using that only we got the electric field here in between the two plates of the capacitor as this much. So now applying this equation, surface charge density here. So actually there is no place here, so I'll have to continue this next step in the, so next page. So I'll just take out the next page. So this is the next page. So now using surface charge density, surface charge, so density sigma is equal to Q by A. So then what happens to the equation now? So V is equal to, we got so previous page, just check the previous page. So V is equal to ED, that is equal to sigma by epsilon naught into D. So this now another very important thing is, this is another very important equation. There are very important 3 steps here in the derivation. First step is the net electric field in between the two plates is sum of the two fields E1 and E2 due to the first plate and the second plate. Actually, both the plates are of the same area. So actually, this need not be written A and A on both sides. Then it looks like labeling. So labeling already it's made here. Left plate is called P, right plate is called as Q. Again, A and A means it's confusing. So area of each plate is denoted as A. I'm just putting that also in brackets more clearly so that it's not doesn't look like labeling. So P and Q are the names of the two plates. A is only area. So D is the distance between the two plates. So it's much more clear now. So the second important step is the result obtained for that is the resultant electric field between the two plates obtained from Gauss law sigma by epsilon naught. And third, equally very important step in the derivation is potential difference is equal to ED. So these three steps must be remembered. So they are very important in the derivation. So I'm just putting the 3 stars here. So this is important. This step also is a very important step. And next, this step also is a very important step. Just by remembering these 3 steps, the entire derivation can be obtained. Now substituting this here, so implies V is equal to, in place of E, we substitute sigma by epsilon naught. Now in place of sigma, what can be written? Q by A can be written. So that will be the next step. So in the next page, I'm just showing that here, just here in this page. So V is equal to ED. In place of E, what is written? Sigma by epsilon naught. In place of sigma, Q by A can be written. So sigma by epsilon naught into, so this is E into D. That was the previous page step. So sigma by epsilon naught, that is nothing but E, electric field into D. So in place of E, we got Q by A. So this will be what now? So A right in the denominator, it will be what? Q into D divided by epsilon naught into A. So this is the next result. So this is only result obtained. So this is also actually very useful to understand on what factors potential difference depends upon between the two plates. Means they got that potential difference is directly proportional to charge on each plate, distance between the plates, and inversely proportional to the area. So this is also very useful for the sake of understanding, but it need not be, so it need not be by hearted. So it's a part of derivation. If required, it can be derived just as we have seen in the derivation, but it will not be usually separately required. So only the final result of this derivation is very important. Now we got the potential difference between the two plates equation. Now already definition of capacity we have seen, that also we have seen in the rough column. Just check the rough column once again. So definition of capacity here, we have seen that capacity is equal to charge present on each plate. So it's positive or negative, left plate positive, right plate negative. So on each side of the capacitor, on each plate of the capacitor, magnitude of charge, ignoring the positive and negative natures, positive and negative signs, magnitude of charge on each side is Q. That is, charge on each side is Q divided by potential difference between the two sides, or potential difference between the two plates, V. So this is the defining equation for capacity of a capacitor, applicable even for the present parallel plate capacitor. In general, for any capacity of any capacitor, this is the equation. So applying this equation now, we already got the potential difference. From electric field intensity, we got the potential difference. Now substituting that here, we can easily get the equation for the required capacity of the parallel. So see the heading. So always compulsorily observe the cursor. So capacity of a parallel plate capacitor, expression for, so that's what is required here, expression. So using the definition of capacity, we can get the expression for capacity by substituting the potential difference here in this equation. So that's the next step. So very simple step. So now from definition of capacity, C is equal to charge divided by potential difference. So substituting equation 4 here, charge divided by potential difference is what? QD divided by epsilon naught A. Now just see here, numerator and denominator, Q is common factor. So denominator Q will get cancelled in the numerator Q once. Then what is there here? 1 divided by D by epsilon naught A. So this can be written simply as, so D by epsilon naught take to the numerator, epsilon naught A by D. So epsilon naught A divided by D. So this is the required or final equation for the capacity of a capacitor. Now capacity of a capacitor, so previously in the definition of capacity of a capacitor, we have seen that the capacity of a capacitor is actually dependent only on the dimensions of the two plates. So in what way it depends on the dimensions? So we are getting the answer for that here. Dimensions means how big the plate is or how big the conducting plate is. So it can be seen that capacity is directly proportional to the area of each plate and inversely proportional to distance. So this is a very important result. So this is the final expression for capacity of a parallel plate capacitor. It can be seen that it clearly depends only on the dimensions, the area of each plate and also distance between the two plates. So epsilon naught is called permeability of free space. Free space means air or vacuum. So between the two plates only air or vacuum is present. So that permeability of air or vacuum is denoted as epsilon naught here. So this is a very important result. So this is the completion of the derivation. So entire derivation is actually very simple. So it's carrying about 4 marks. So here this page actually there is no change at all. So as it is, all the steps are present here. So in the previous page, just see, look at the previous page once. So little entire derivation as it is, it can be taken. So rough column must be taken. Rough columns are always very important. So any doubt comes in the derivation, rough column steps will be very useful always. So this rough column steps must be taken on the right side of the page in the classwork. Now how to write the running notes? Running notes is very simple. So I'm just making it more simpler here. Just here. The running notes is very simple. So as it is, the derivation will be coming without any change at all. But here just 2 or 3 introduction lines should be given. Now firstly, parallel plate capacitor definition. So this is the definition of the parallel plate capacitor. So that will be coming here first. So it is a capacitor. So as I'm giving now I'm giving a little time for writing the running notes. So very quickly the running notes must be just within 5 minutes it can be completed. So don't think that I'll complete later, I'll take the snapshot and complete later. No, now while listening itself the running note should be completed because it takes only few minutes to complete it. So only just 2 or 3, just 3 or 4 lines I'll be just adding it here, adding them. So that's sufficient, and all the remaining steps will be same as we have seen in the derivation. So there won't be any change in that. So it's a capacitor having two identical plates like this, like the rectangular plates here in this diagram, rough diagram, having two identical plates parallel to each other. So this is the definition. So next, the actual derivation. So actual derivation diagram, everything follows from the diagram. So P and Q are the two plates of a parallel plate capacitor. So don't delay. So now itself write the running notes. So once you are watching a particular class video, immediately you should complete the running notes, whatever running notes belong to that particular class. Later you should never watch the video again. So you have to spend time on finding out the reasons for different steps of the derivation. Certain reasons will take lot of time, and very though the point might be very small, but still it will be actually really very important. Such minute points, tiny points in a particular derivation, you have to be thinking. Any doubt is there, you have to find out the clarify that doubt. You have to find out the reason behind that. Using every reason will be directly based on the previous topics of the same lesson. So here most of the things are entirely based on electric field intensity, the Gauss law, and the potential difference. On these concepts it will be depending upon. On such things you should be spending time, but class you should never be watching a second time. So first time itself you should watch fully, and immediately you must complete the running notes from the board examination point of view. Even those who are preparing only for entrance examinations, they also must take all the steps of the derivation, because from each step of a derivation infinite number of problems can be set. There's no limit to setting of the problems in the entrance examinations, but every problem can be solved if the derivation steps are known thoroughly. So P and Q are two plates of a parallel plate capacitor. A is the area of each plate, and D is the separation, that means distance between the plates. So next, a battery. Actually, there is no place here, so I'll just write very small letters. A battery charges the capacitor to a. So this is just you see, I'm writing very small letters. So but I'm pronouncing the words clearly. So as I'm pronouncing, you must complete the running notes. Later the words can't be understood because they are very close. The battery charges the capacitor to a PD of V. So charges are, so what are the charges on the two plates? Plus Q and minus Q. So plus Q and minus Q are the, so here also you just see it can't be understood later, now only it should be written. Plus Q and minus Q are the charges on two plates. That's all. So next, E is equal to, what is E here? Net electric field. So I'll just move the equation a little low below. I'm just moving the equation to a little below so that one sentence can be written. So this way. So there is no problem here. It can be understood. It will be neat only. So next, the electric field so between P and Q. What is the electric field between P and Q? E. E is equal to E1 plus E2. E1 is the field due to the first plate, so that need not be explained. That's understood here. Next, from Gauss law, E1 is equal to sigma by 2 epsilon naught. E2 is also sigma by 2 epsilon naught. As sigma is equal to Q by A is same for P and Q. So here also actually sigma is equal to Q by A, surface charge density. So here actually it should be, if it is written clearly, it's better. So I'll just as surface charge density. So density I'm writing in short, see. So actually when you're writing, you have to write in full words. As surface charge density, sigma is equal to Q by A, same for P and Q. So here firstly surface charge density is coming, and the same thing we have used in the after this step also. So substituting all this, so these are the various steps. So here there is no change, as it is they can be copied. So now these steps as it is they can be copied, and in the next page also, just see the next page, the steps will be coming as it is. So using surface charge sigma is equal to Q by, actually this need not be written again. So but still for the sake of clarity, we did not number that one there. Sigma is equal to Q by A, actually it's numbered by an equation, just we can just say using, instead of that directly this also can be written, no problem. Only half step extra is coming, so it doesn't matter. So these are the steps of the derivation. So entire derivation is very simple. So running notes also, now within 2 minutes you can complete the entire running notes in order before going to the next topic. So now put the video to a pause, and just whether it's 1 minute or 2 minutes back, you just rewind it and put the videos to a pause and then complete the running notes before attending the next topic.